It now has the audio that says this meeting is being recorded. The first time I heard that, which was like a couple weeks ago, it kind of freaked me out, but now I know that happens. So again, you can follow us at all these places. You can stay connected with me, Sage Elliott in most places, 2 L's and 2 T's on LinkedIn, Sage Codes on Twitter, where you can get all the links at sageelliott.com. Here's all the kind of handles for our company, Plainsight. And again, we were 6skill, now we're Plainsight. Hit record. I already hit record, so we're going to skip the slide. Setup, again, for anyone who just came in, because I do see people still trickling in. All you need for this workshop to follow along is a modern web browser like Chrome, a Google account. Collab, which is the tool we're going to be using, is made by Google, so you need an account to run the code there. And then sign up for the labeling account. That's how we're going to label our data at Plainsight. All right, so what this workshop is, this is a hopefully very friendly introduction to computer vision, kind of designed with no previous experience expected, but knowing some Python will be helpful when we get to the coding portion, or just not being afraid of some programming stuff. So we will cover applications and basic intuition, how to label your own data, and then jump into the code and train a model, and then run that model on some images and videos. Just keep in mind, you can't learn everything in 2 hours. So we're going to cover a lot, and depending on your background or experience, it could be really fast paced. Maybe you might, when you get to the code, if you've never done Python before, it might seem like a lot, but that's okay. You can or you can learn a lot by sticking through it, I think. And then the most important thing is to kind of keep learning after workshop. So I would suggest train your own model, bring in your own data, and you'll learn a lot by doing that. A little bit about me. My name is Sage Elliott. I'm a machine learning developer evangelist at Plainsight AI. We do really cool stuff with machine learning, computer vision, and IoT across a whole bunch of different industries. And we also create tools to make it easier for everyone to do the same thing. For about the past decade, I've worked in software or hardware with startups and agencies around Seattle, and then also Melbourne, Florida. If anyone happens to be from Central Florida, let me know in the chat. It's always fun hearing about, there's almost always someone in there. I really like making things with technology and like working with hardware and combining everything together. It's really cool. Again, you can stay connected with me at LinkedIn or Twitter, Sage Elliott. About you. So normally doing like a workshop in person or something, I'd have you go around and introduce yourself here. But there's already about 100 people in here, so that would take too long. But it is really fun to communicate in the chat. Where are you watching this from? I know some people did it earlier, but now there's a lot more people in here. If you want to throw in the chat where you're watching from, it's really cool to see where everyone is sitting right now. And also feel free to throw in why you're interested in computer vision. It's always really cool to hear if someone has a project or something specific that they're learning. And I'll share this in the chat. This is a link to the Slack channel. So I'll be in there. You can also introduce yourself in there. Trying to get more communication happening in there. But I think it's a cool place to kind of start growing a community and share what you're doing or ask for help or questions. So there's a whole bunch: Austin, San Francisco, Dallas, Iran, more Austin, Melbourne, Australia, Portland, Silicon Valley, Atlanta, Georgia, Montreal. Awesome. I love seeing everyone, like where everyone is. It's so cool. And like I was saying earlier, it's one of the really cool things about doing virtual events is being able to connect with so many people, which is really cool. And again, if you want to join the Slack, I'll wait a second and post this link again in the channel. Someone said they were in Renton, Washington, which is not far from me. And you had a cool sounding reason. I lost it, but really cool seeing where everyone is. Someone said they want to be more marketable when getting a job. That's a great reason. Someone said Bellevue, Washington, essentially right across the lake. Someone's from Seattle. Hello. All right, we'll keep going. Again, really cool to see where everyone is from. Setup for anyone who just came in, because I think some people did trickle in. We'll be using online data science coding environment called Collab. Again, maybe you've used it before. If not, you just need a Google account to run the code. And you can sign up for the data annotation tool here. And then you should be good to go. All right. So what is computer vision? It's a pretty big field, but essentially I would boil it down to how computers gain understanding from images or videos. So here's a little example. It's a model we've trained to detect trucks. Then it's also detecting when it's moving versus stationary. And you can see there's a couple things going on here. You can see this little box drawn around the truck. You can also see pixel by pixel, it's trying to draw exactly where the truck is. And we'll talk about these more in a second, but the rectangle part around it can kind of be referred to as object detection. You're drawing where something is in the image. And then this pixel by pixel part is segmentation. So you're drawing exactly where something is. So the rectangle is drawing like a rectangle around the entire object. The segmentation is drawing exactly where the object is within the image. And you can see, this just has another layer that you can tell when an object is moving from frame to frame, essentially, and classify it as a moving truck versus a truck sitting still. I also want to note that there's other types of data that can kind of be used as images or seen as images. So for example, you've probably seen some sort of visualization of audio, right? So the audio signals or the audio waves get turned into kind of an image, and then you can actually use computer vision to look at those and do things like see what type of sound this is, or maybe see what kind of word is being said in the audio. And then also you have things like LiDAR data that's like 3D like point clustering, and that's kind of considered computer vision as well. One reason why I love computer vision today is just it's a really cool interface into the world. And today there's just a ton of people using computer vision across all the different industries, and it's making a really big impact in a lot of them. So who uses computer vision? More and more companies are using it just across a whole bunch of fields. So first, just to talk about a few that maybe you've experienced before, Amazon, they have Amazon Go. Actually, let me know in the chat, has anyone been to an Amazon Go before? We have several in Seattle. I know there's some in other states, but I know they're not super widespread yet. Really interesting experience. You go in, it's kind of like a convenience store or a small grocery store. And if you look up, it's all just cameras and arrays of, I think, some sort of GPU or some sort of processing unit. And it uses computer vision to do everything like checking out. So you walk in, you can grab a piece of fruit, you can grab something off a shelf, it uses computer vision, it assigns that value to you, and then you just walk out of the store, and it kind of feels like you're stealing the first time you do it because you didn't have to stand in line or anything. But they have delivery robots they're working on, self-driving cars. They bought a company called Zoox last year, and they also can use computer vision to look at products uploaded on Amazon.com. Google Photos. If you have Google Photos or used it before, you can search for like something like dog, and it'll pull up all the pictures of the dogs you have. YouTube content filtering. There's an insane amount of video gets uploaded to YouTube like every minute, and they need some way of kind of monitoring that. Self-driving cars. Again, Tesla, self-driving cars. Facebook, you probably upload an image if you have Facebook, and it'll be like, is this you? Is it your friend? It can be a little creepy sometimes. So these are all things we've probably seen or know about in some way, but I don't want to talk about some of the really cool fields too. So some like agriculture, you can do crop and animal monitoring. Construction, you can do site monitoring. And I've seen companies working on self-driving tractors, which sounds really cool to me. Manufacturing, this is actually how I got into computer vision. Was I was working at a company doing manufacturing. We had a really complicated part that it was hard to train someone to classify if it was good or bad. And I thought maybe I could just use computer vision. Turned out I could, which was really cool. And then it just got me really interested in the field, and I kept learning about it. You can measure things like throughput, supply chain, worker safety, oil and gas. You have leak detection, safety, healthcare. Someone was talking about how they wanted to learn computer vision today to do some stuff with X-ray images. So like X-ray diagnostics, MRI scans, medical research. Does anyone have any fields that I missed that you want to talk about computer vision being applied to? There's a ton of them. This is by no means all of them, but these are the ones that kind of stick out in my mind right now. Someone said Hudson is starting to integrate Amazon Go in a few airports. Oh, interesting. That's pretty cool. Someone said Apple's new object capture feature. Someone said insurance, retail, satellite imaging, logistics. Retail is a really cool one actually too, right? Like measuring where people spend time in a store, how to change displays and stuff like that. It's really, really interesting. Someone said water assessment. That sounds interesting. I did not think about the water industry, but it's so cool seeing all these different things, right? Like there's so many different fields that you could use computer vision in. So it said license plate tagging. That's a big one, right? Like for security or even with, I mean, right? Like if you go through any checkpoints right now or toll booths, I think there's some sort of computer vision there grabbing license plates if you don't pay. Drones. And this is so cool. There's so many great applications people are putting in today. Sometimes people only put a couple. So it says social media. I like the water pipeline one. Sounds really interesting to me because that's just one I don't think I've heard someone bring that up before. So that sounds interesting. Like water assessment. I wonder what type of stuff you could do with that. I'd love to learn more if that's an industry you're in. Right. So we're going to go on. Computer vision and deep learning. So computer vision isn't always tied to deep learning, but in the past decade or so, deep learning, the field of computer vision has pretty much been dominating all the complex problems. So if you hear about a company doing something really cool with computer vision, chances are it's using deep learning behind the scenes. So other intros will usually cover kind of the intro of deep learning aspect more in depth. But I just want to give you a very high level of kind of what's happening, just so you know, like why we're making, why we're labeling data and why we need it to train a model. So you could think of the model as being like a function, like a big programming function or a mathematical function. And what we want to do is we're going to feed it training data. So in this case, a lot of times computer vision is like a supervised machine learning problem. That means that when you're giving the data to the model, you need to give it labels as well. So for example, let's say we're going to train not object detection. We'll say we're going to train an image classifier. So we could give the model images of cats and dogs, and then the correct label associated to those images. So we'd give it an image of a dog with the label dog, and we would give it a whole bunch of images, and it would look at it a whole bunch of different times, and would start learning what features in these images make up a cat or a dog. So it's going to like look at it maybe thousands of times and then say, okay, cool. I think I can be pretty accurate now if I look at a new piece of data. Then we're going to feed it a piece of data it's never seen before, and then hopefully get the correct prediction returned. So just a couple links if you want to explore this more. We won't go too deep into like neural networks here, but there's kind of a cool site there if you want to play around with a neural network. And this is a cool site visualizing a convolutional neural network. Quick note on transfer learning. So with most popular deep learning frameworks, you can load pre-trained weights. So that means that it's already been looking at a whole bunch of different images, and you can take this kind of pre-trained model, then feed it your own new data. And even if your new data is way different than the data that it looked at previously, it turns out that often this helps a lot in training your model. It makes it a lot faster, and you often need less images. So you'll see this today. We're going to use transfer learning. You can just think of it as really, we're not starting from zero with our project. So we're going to train a model, and it's only going to have a couple hundred images, and you're going to see it actually works pretty well for our use case here. So it does depend on your images and the complexity of your data, kind of how many images you'll need to feed it. But kind of as a good rule of thumb, just to start getting some results, I suggest a minimum of like 200 kind of for hobby projects. Chances are you'll need more to get really high accuracy if you're doing like a enterprise project. You want to deploy it with, whatever really high accuracy you need. But if you're just getting started, don't worry too much about it. Just label some images and kind of see what the model learns from it. We'll talk more about data sets when we create them as well. But really, just for now, think of transfer learning is not starting from zero. So some types of computer vision. The computer vision field is really big. We're going to focus on computer vision with deep learning and kind of the most common types that you'll see out in the field or that you might use to solve your types of problems. So you have classification. We talked about this a little bit for the deep learning example. Classification is often trained on a whole image or sometimes the portion of an image. So if they, if you were to, crop a certain part of, and always look at a certain portion of an image, what that does is, like in this case, I trained a model to detect the dog breeds. I gave it this image and it just says, hey, I think it's a Labrador Retriever. But if there was another dog in the background, it might really throw off the model, or maybe you want to know what both dogs are, and the classification algorithm can only look at this whole image or a specific portion we tell it to. So that's when you kind of want to go into something like object detection. Object detection can classify and localize where an object is inside an image or a video. So here, this model can detect geese. We're actually going to build this today. And right, it's saying there's a goose and it's estimating where it thinks the goose is inside of the image. And it thinks there's another goose over here, which I mean is correct. So instead of just saying, hey, a goose is in this image, it's saying, I think there's a goose here and I think there's a goose here. And so we're going to make this today, which will be really cool, especially if you've never done anything like that before. We have instant segmentation. So kind of like object detection, instant segmentation can classify and localize where something is in an image. And it might be hard for you to see, but kind of like that truck example before, it has a rectangle drawn around it, but also the precise pixels where it thinks the actual object is in the image. And what's cool about that is, one, if you're training for instant segmentation, sometimes it can increase your accuracy versus just object detection. It tends to be a little bit more accurate when you're you'll see how it will label for this, but you're training essentially more precisely. But also you can do cool things with like pixel interaction. So in this case, we're measuring the pixels of the bottle and we're measuring the pixels of the water here. And you could do a calculation based on that, how full is the bottle based on how much water is kind of overlaying the bottle. Or one example I like to bring up is if you're doing something like in VR and you're doing a VR keyboard, instead of just detecting the entire hand, you want to know precisely where all the points are in the hand. And so if you touch the virtual key with any finger, you could press it versus just having a rectangle drawn around the whole hand. Feature point clustering. It's another really common one that you'll see out in the field or that you might need to use. So here we have the kind of a skeletal structure labeled of all the joints in the human body. So it's like looking at the neck, where the head is, where the arms are, and it can actually calculate kind of, in this case, what yoga pose they're in. This is also pretty common for face applications. So if you've ever seen an example of a computer vision facial application, you'll see things like points drawn on the face, like eyes or mouth, and you can do things like estimate the mood and stuff, which is pretty cool. Image captioning, you can actually kind of combine different types of neural networks together. So you could use computer vision to look at objects in this image and then actually kind of understand context of it. So instead of just being like, there's a beach, it could actually, have some sort of context understanding of like, there's a child on the beach flying a kite. Generative deep learning. I think this field's really fun. I did a fair amount of kind of fun work in this with something called a GAN. You can generate fake images. I'll just share a link if you want to check out this project I worked on at some point where we were creating houses, or like we scraped images of a famous architect and then trained a model to trained a model to create original drawings kind of based on their style. And it was a pretty fun project I did with an architect. And then also I'll share a link in there. This just kind of talks more about GANs and it shows some examples of really interesting ones. So they look like realistic faces, but they're actually generated. And it can be kind of creepy how accurate they could be. And then these images here actually came out of this project I was working on. Before they started looking like houses at all, they actually looked like really cool space art. And so I thought it was really cool. You can also do like generating art, which is really fun. I see someone shared in the chat, thispersondoesnotexist.com. That's a cool site where it'll generate I think it generates a human every time you go to it, but they don't exist. It's all from a GAN. So choosing a model. There could be many use cases for different models and ways to tie them together. When getting started, think about, what is the problem you're trying to solve and what are the outcomes you're looking for? So do you, just need classification, like understanding if there's a dog in there, or do you need, more precise things like how many geese are in the camera view? In this case, there's another example. It's trained to detect this mice and a piece of food, and when the pixels overlap, it classifies it as feeding or not feeding. There's a lot of factors that go into this that I can talk a little bit about in a second as well, but efficiency is a big one as well. So if you know you're going to deploy to a much more stringent hardware device, that is something to think about, like, is there a more efficient object detection model, or can you use just classification versus doing something like instant segmentation tends to be slower and more resource intensive. So sometimes you just have to kind of do a trade-off depending on what you're trying to do. Object detection in a gist. So if you want to read way more about object detection, I will share this link. But essentially, we train a model, and then it's going to kind of find proposed regions in an image where it thinks maybe that object is. It's going to run a classifier that's trained on our data, and it's going to calculate an estimate of the location. So it might be like, cool, I'm pretty sure, the goose is within here. I looked around. This would be my estimate. And you'll see, sometimes it can be pretty good. Sometimes it can be off. It depends on your model and how much data and how well you label it. So some popular object detection methods. We have single shot multi-box detector, or abbreviated to SSD. It does object detection. It does it very fast. You have you only look once, or yellow. It also does object detection and it's fast. So again, remember, object detection is kind of just drawing the rectangle around it. You have a mask-RCNN, or a faster mask-RCNN. It can do the object detection. Instant segmentation tends to have higher accuracy, but is slower often than these ones. And I do remember a new version of yellow came out recently, and I can never keep up with like the benchmarks of that versus single shot multi-box detector or anything. And so maybe I'm wrong now, but I think that the single shot multi-box detector is tends to be lighter weight. So if you are trying to deploy onto some sort of edge device and you don't have a ton of memory or GPU or something, you might want to choose like this over, YOLO or the mask-RCNN. And then we have a Facebook Detectron 2. So what we're going to use today, open this up. Detectron 2, so it's a PyTorch-based kind of essentially a wrapper around PyTorch that makes it even easier to train a model. So I'm going to play this video real quick, just kind of show what it can do. So you'll see it fades into object detection here. It's detecting all the things on the table, even has chairs. And then it's going to show these people. It's doing the feature points, kind of like we saw before. And then it has this cool thing built in called dense pose, where it actually kind of does a little bit more than feature points and estimates, like a 3D character of it. So I've seen some people, trying to use that for like a game generation or something, which is pretty awesome. And they have instant segmentation. And then you also have the version of instant segmentation, I forget the word for it, where it's like every pixel in the image is segmented out. So you can see before it's kind of doing these common objects. And then when it goes over to this other version, it's covering literally every pixel in the image. So it's saying like, I'm estimating all the backgrounds of stuff is a cabinet or a wall tile. If this is outside, it would say like sky or city skyline, whatever is in the background. So this is what we're going to use today. It has a lot of really cool built-in stuff to kind of easily train for object detection or instant segmentation, and using transfer learning, right? Like you could also just take in these model weights and run it and see how well it does on your data set. Sorry, any questions so far? I'm going to take a quick break, catch up on the chat, because I see some stuff in there that I did not get to. Again, I apologize if I accidentally miss anything in your chat. Feel free to ask it again, because I'm not trying to purposely ignore you. But sometimes too, if people keep talking, it kind of just pushes everything up. Any questions in the chat? Someone said, any good resources for getting training images? I don't have a single one. Like it depends on what your project is really. because, oh, sorry, I did not do the Facebook URL. Depends on your project. So there's a lot of open data sets on like kaggle.com, or Google even has a search function or a search site now for finding data sets that might fit your need. But there isn't, like, it just really depends on what you're looking for, I guess. But Kaggle or Google search would be the first I'd look at and see if there's already an existing data set for it. Someone said in a factory, though, you have to have such reliable training. Yep, that's what I was saying. Like, for getting started, if you're building your own thing, if you have 100 images, put it in or something, but you'll want to look at the metrics and see how accurate it is on data it's never seen. And yeah, if you're doing stuff, especially like, I mean, imagine doing a self-driving car. Like, you can't have a self-driving car that's that's not very accurate. So if anyone's like safety is at risk or anything, it's a whole different story. Someone said, will the recording be available after the presentation? Yep, I'm recording it, so I will share it out in the email. So if you signed up on Eventbrite, you should get an email afterwards. Not right afterwards, I'll try to get it up in a day or two. Someone said, was it a little late? What programming languages are being used for this? We're gonna use Python. Someone mentioned that I mentioned audio can be segmented like images. So I don't have an example right now, but I think it's called a spectrograph, where you change audio into an image. Like, you've probably seen examples of this just like for audio visualization somewhere. And if you imagine that, like, all different stuff has different waveforms, like maybe a word and stuff like that. So you can, there's ways that you can train kind of a computer vision model to look at audio and get things like words or specific sounds out of it. Someone said, is there a specific library for that to turn audio into images? I'm sure there is. I don't know one off the top of my head or remember. But if you Google it, I'm sure there's more than one option. All right, I'm going to move on. I see some other questions, but I'm going to continue right now, and then I'll try to catch up in a little bit probably. Because I want to get to the little bit more hands-on part. We're pretty close. All right, so the full computer vision lifecycle. Today we're going to do the data annotation. We're also going to do the machine learning part of it. But really, there's kind of this whole lifecycle. So it really depends on what you're doing, and if you actually need to deploy this out in the field. But you might have things like device management. So usually that's like managing like edge computing resources or sensors. So in this case, like cameras. You have data collection. It's managing data from those sensors, like the camera, putting those in some space where you can then curate a data set. Creating data sets, sometimes that could be web scraping. Then you have the data annotation, or called labeling, machine learning, so like model selection and training, which we'll do some of. And then you have deployment after that. How do you deploy that model out and run new pieces of data on it? And then you kind of want to repeat it for continuous machine learning. The reason why, or a good example I always use for the continuous ML part is, imagine that you were a store, something like Amazon Go, or where you're looking at people and you want to have a really accurate model. Well, if you take all the data from the summer, people might be wearing shorts and tank tops. Maybe they have baseball hats on or something. And then the data in the winter might be people wearing winter clothes. So they have like scarves, giant coats, big boots, way different hats or something like that. If you only trained your model on the data from the summer, then it probably would not do very good on the model, or sorry, on the data in the winter. So it's kind of important if you have like a model deployed out in the real world and you're kind of constantly running it, it's kind of important to kind of keep repeating the cycle with new data, and you avoid what's called a model drift. And not going too far into it here or anything like that, but if you're interested in kind of seeing any of that like all in one platform, it's kind of the next step of our platform is going to be adding in the training and deployment pieces. So after you label, you can kind of train, select some hyper parameters. If you want to see anything like that in a demo or something, you can let me know, or you can just contact us in the contact form there. All right, so let's go and do some of the hands-on labeling. And while we're setting this up, I'll try to catch up on chat again. So I'll copy this link again if you want to create the account here. My mouse is being weird. That's the link. You can sign up for a Sense account. And once you sign up, it'll take you to a page. I think you have to verify your email. So it'll just send you an email with a link to actually sign in. And then once you do, you should get to a blank page. Mine has some projects in it because I've been using it to do some labeling. And I'll give everyone a minute there, and I'm going to catch up on the chat. So there's a lot. So again, sorry if I missed some. I think someone was talking about self-labeled training set. Actually talk about that in a little bit. So one feature that's coming out soon in here that isn't quite here yet. So I'll show you, there's something called auto label where you can select a pre-trained model on specific classes and then have that automatically label your data set. But there's no perfect model, right? Especially if it's not specific to your data set. So it can try to do a pretty good job, but it probably won't be perfect. So you kind of want to supervise it, like, or you want to review the data as it's labeling it and fix any errors. And then soon what will be coming out though is you'll be able to label your own data set, train a model, tie that model back into that feature, and then it will label the data, which will be cool. Label the data for you. All right, so let's see. Oh, someone asked, can you make this work with moving images, etc.? Camera embedded in a pair of glasses. Can a moving image? I mean, are you talking about like video, right? Yeah, you can totally do kind of object detection and stuff in moving videos. I think that's what you're talking about. I think you're talking about maybe it's on you, so you're moving around, but you can totally do those types of detections just, as long as you have a good data set for it. And if you're thinking about building it, I'd love to see an example. That sounds really cool. All right, so if you signed up here, what we're going to do is just kind of create a new data set. Also, you don't have to follow along with these specific images, but if you do want to download the exact same samples I'm using, I'll link to it here. So I'm going to create a new data set. So this is, again, even if you don't follow along right now, it's cool to see all the steps here because this is what you're going to do, well, hopefully after this workshop on your own data set and then, train a model. So once you're logged in, just hit new data set. Someone asked if that link goes to the slides. No, that's a link to the example images I'm going to use here, but I can share the link out to the deck in an email as well. All right, so I'm going to name my new data set. I'll just say workshop. You want to give this a meaningful name though, like geese or whatever you're training object detection on for. Hit save and continue. Sources, hit add source. I want to upload local files. I'm going to choose local files here. And I have some images I already downloaded. Again, those are the ones I shared the link to if you want to follow along or just try this out later. But again, you could try it on your own data set because that's actually when you're going to do cool stuff. I'm just going to show off how to do all the things I think you might want to know how to do. And then just noting, so we can connect to Google Cloud Storage and Amazon S3 buckets. So if you don't have local images, most corporations actually store things on something like GCP or S3. And also a cool feature that's not in the local file part yet, but will be coming soon, is being able to automatically break down videos. So if you have videos stored in your S3 bucket and you connect to it, it'll give you a prompt that's like, how many frames per second do you want to break this down to label, which is a really handy feature. All right, so let's go to our label definitions. And I'm going to make a few here. So just kind of showing you different examples of how to do different types of labels. So I'm going to call one goose, and I'm going to leave it as a rectangle, but you can change all the label types here. Again, so like rectangles is how you would just draw for object detection. Polygons, for instance, segmentation. Points are feature points for feature point clustering. And then we have like classification and stuff in here too. So I'm going to leave this one rectangle. This color doesn't really do anything except for it's for you as the labeler. This is so like if I know the geese are on a green background, blue might show up better. So I'm going to leave it blue. And then we have an auto label option here. And I'm going to show off how to use this feature in a little bit, but I'm going to leave it blank for now. But you can do the setup for this feature here as well. So I'm going to make another goose just to show the difference between rectangle and polygon labeling. And I'll leave this color. Hit save. And I'm going to make one called cars. I'm going to make that a polygon as well. Make this color a little brighter just so I can see it better. And I'm going to have one called cups. That's going to be polygons as well. A lot of people work with polygons because either you're doing like segmentation tasks or you're trying to get that extra few points of accuracy. And what was the last one I made? Cups, I think. So then I have another one. I'll do PCB, printed circuit board. It's like a use case for manufacturing, like I've done in the past, and maybe something like PCB damage. So there's some damage on that board, and like we want to label it. So again, these are just going to be kind of several different examples showing off like how you would do this for what hopefully it's going to cover kind of something that can transfer to whatever your use case will be. So at the bottom here, if you scroll down, we have this area I'm going to leave blank during this workshop, but it's really cool that you can add instructions here. This is really important if you're working with a team or if you're working on a really complex problem or like you have a lot of different labels and you want to remember what is what, you could write it down here. And it's also important, a lot of people don't think about it, but even if you are doing the labeling and you're like the machine learning expert or something like that, you might not be the domain expert of whatever you're labeling. So for example, someone was talking about x-rays earlier. I don't know if you're in the medical field, but like I wouldn't know what a specific type of tumor looks like, or fracture or something like that. I would want to have a doctor go through, probably do some of the labeling themselves, some good examples, maybe some bad examples, and then keep those here as a reference. So as I'm labeling or people on my team are labeling, I can reference this and make sure I don't make mistakes. So for now, I'm going to leave it blank, but it is a nice thing to have if you're doing teams or a complex problem. So I'm going to hit save and start labeling. And this will load in our images. And you can see we have this image of a goose. You can zoom in and out using your scroll wheel. You can pan around to the image by clicking and dragging. You have some other things here. So if you accidentally scroll like way too far out or you kind of lost the image, you can hit resize to fit, and that'll just bring you back here. All right, so let's select our image for rectangles like we were going to label for object detection. So if this is kind of the traditional way of just labeling for this, you want to draw these squares or rectangles around the objects, in this case, geese. So we're saying, draw a rectangle around every goose in the image. It's really important to get every one because if you had another goose here, and you only label these two, but not the third one, and we train it, we give it to our model and it's training, it's gonna be like, cool, you're looking for these features, right? You're giving me these labels of what I should learn to look for. And then it's gonna look over here and make a prediction that's what we're looking for, and we're gonna say no. So it's gonna really confuse the model. So it's really important to train or to label every instance of the object that you want to detect as you're labeling. One caveat to that maybe is like, if there's a goose way back here and it was really small, and we're okay with our model missing it, maybe we don't label it there, but it's pretty important to get every instance. So if they're, again, keep that in mind as you're labeling. And usually you want these to be, as close to the object as possible. So if I, was like drawing a box, but it was really big like this, our model would not be as accurate. So you kind of want to very neatly draw these boxes around where a goose is. And that's what we do the manual way of labeling for object detection. So I'm going to show polygons. If I select the lowercase goose, which is a polygon here, the traditional way of labeling for polygons, or kind of this instance segmentation, is you want to trace around the object. So I'm going to do a terrible job here because it takes me forever to draw around, a goose. And this isn't even like that complex of a shape, right? But it's still like, again, I'm not doing a good job. You want to be really close to the object, kind of like boxes, except for it's around the entire thing. So you can see though, even doing a terrible job, this is taking me way longer than, labeling the rectangles for object detection. Again, this is an awful job. Don't hire me as a manual data labeler. So you can see like sometimes like when in the past, I've even been like, oh, I want to do segmentation or something, but I don't want to label hundreds of images like this because again, we have another instance here we didn't even label. It can take a long time. So I'm going to delete this. I'm going to show a really cool feature. This is one feature that came out that I was so excited about, and I use it all the time now on almost any kind of project I do. So we click this little box. This enables what's called Smart Poly. And then you click the label. And then just kind of like you were doing before for object detection, we're going to draw a rectangle. And you want it to be very close around the object here. And then just click. And you can see it snapped a polygon to it, which is awesome. So way faster than manually drawing. Let's go do it here on this other goose. And you can see it wasn't perfect here. It actually did a pretty good job. But like my eyes, if I zoom in, I have trouble telling that's part of the goose and not part of the sidewalk, but I can kind of infer that it is. So if it's not perfect, I can come in, I can get all these different nodes. When I click on the label, just click on this, I can just drag it how I want it. You can also delete these, so you can highlight this node and hit delete or backspace. You can also add nodes by clicking this. Someone asked, does this only work with high contrast images? No. So like it'll probably work better with a lot of high contrast images, but I've actually had it work in some surprising use cases. I would say try it on your data and see if it works. Sometimes it won't work as well as other times, right? But it's not just looking at contrast. It's actually a model behind the scenes that has learned how to segment out stuff. So I've actually been really surprised sometimes, being like, I don't know, will this work? And it did. So the best answer is to try it on your data and see how well it works. But you don't necessarily need to be like super high contrast all of the time. But that does usually, if you're high contrast, it'll probably do very well. All right, so let me delete these again, and we'll move on to some different label types. But first, let's go back to our goose rectangle label. I'm going to turn on the auto label feature. So I talked a little bit about this before. We don't have a class for goose. We have 81 classes in here you can choose from. So we don't have a goose one, but we have a bird one. So I'm going to see if the bird, generic bird detector will work here. And I'm going to hit OK. It's going to apply the label and automatically drew those boxes around the geese. So then I just hit submit. That's when I'm done labeling this image. It went to the next one. I already have auto label here on, so I can turn it on and off like this. And it found those geese and applied the labels automatically to them. So if the model that we have here that will work in your use case, so if you're looking for birds or geese or something like that, you turn on the auto label and then just kind of hit submit. Make sure that it labeled it correctly, and then hit submit again. And you're essentially kind of just QAing your data as it's being labeled, which is really cool. And like I said, again, coming soon is the feature to train your own model, because using a pre-trained model from someone else, it could do really good sometimes, but if you have specific data that wasn't in that model or something more complex, it might not work very well. So let me disable this. We'll go into the next one. Here's an example of cars. I'm going to take our car polygon, and I'm just going to turn on auto label off the bat, and I'll type in car. You can add multiple labels here. So I know there's one for truck as well, and motorcycle. So this is like, maybe we just want to get everything that might be on the highway here. So I'm going to hit OK. And it found the car. It applied the label to it. I'm just going to hit submit. And this is kind of like if I have a big data set, this is kind of how my approach to labeling right now is. I'm going to see, does auto label work well for it? If it does, awesome, because I'm going to turn it on and then just kind of QA and be like, cool, it's labeling all the cars. And then here's a frame where for whatever reason, it just doesn't like this angle of the car. So it didn't label it automatically. And then I can come in, I can turn on Smart Poly and use it to label the few manual labels. There's an edge of a car here too. So I'm just going to label that as well. Hit submit again. For whatever reason, these angles are doing it for the model here. And this is going to be really useful to train your own model. It'll be much more robust to your specific use case and angles. So here, again, label, and then, it's working there. So it's really just a few frames I had to label manually there. Otherwise, it's like, can I just let the machine learning models do it for me and QA it, which is awesome. So just one last feature kind of for the segmentation, one last kind of AI powered feature is we're going to label cups with a polygon. I'm going to turn on smart polygon because now that we have this feature, I don't like drawing polygons manually. I'm very spoiled. So I'm going to label both of these cups. And then I'm going to turn on track forward. And what this does is it's not auto label. It's doing a form of object tracking. So we gave it 2 labels, and this would be, it's thinking that this is going to be a sequence of frames. So like from a video, right? Like you would break down a video, upload it here, and then say, cool, there's an object moving around or several objects, and they're pretty close together in a sequence of frames. So we can use object tracking. So it knows there's 2 labels, and it's going to look at the next frame and just kind of automatically try to predict the thing that we labeled where it is in the next frame. So you can see here, we're changing angles. It's not super drastic here, but it is tracking the cups, which is cool because it's not a model trained on cups specifically. It's actually just kind of a generic object segmentation with tracking, which is really cool. And then, so if that works on your data too, it's awesome because you just kind of label a couple things or one thing in your data set and then have it track forward. And just an example, I'm not really going to use any of the smart features here, but you can also manually draw the polygons and everything to if you need to. So the smart poly probably would work on segmenting this rectangle, but it's pretty easy to go ahead and draw it. And then something like a scratch in this crazy background, I don't think it would do a good job segmenting there. So if we wanted to do, oops, I did it backwards, but if we wanted to label our PC damage or something, right? Like you still have these options of doing the manual drawing as well. And so you draw and you loop around until you're around the thing you want, and then just connect the last dot, and that'll create your manual polygon. Once you're done here, let's go ahead and submit this. We're going to export our labels. So first, if you want to, you can review them. A lot of tools will have kind of some sort of, or I don't know if most of them have a review option, but you can come in here. You can go back to your data labeler. By default, when you go to labeling or labeler, it's going to show the pending ones. So since we submitted them all, you don't see any in here, so we can select submitted. And then you can manually go through and approve these. So if I'm like, yes, this looks good, approve, we could do that. Or if in this case, we did all the data annotations ourselves, so we trust ourselves, I just want to export data set. And then we can select the format we want here. So the format we're going to use today is Cocoa. Don't worry if you didn't actually do any of the labeling. I'm going to give you a labeled data set with like a couple hundred images of geese. But I just want to show all the ways that you could label your data. So we're going to use Cocoa. So if you're going to do this workshop and then do your own model afterwards, you could label all the images in here, hit export, and then make sure you hit this Cocoa format because that's what the Collab notebook is set up to do. But we have other formats in here that are pretty common. Like if you've done computer vision before, you might have used something like Pascal VOC or a YOLO data set or Apple's Create ML. And then we have a generic JSON document. So if you want to build your own data loader for any pieces of data, you could just use the JSON. But most frameworks like TensorFlow and PyTorch have built-in functions to read in Cocoa datasets, which is awesome. So we can export to Cocoa and then just use a pre-built function most of the time. This is also important. So if we are just doing submitted annotations and not the approved ones, like we don't have that review process, we are just going to check this box, submitted annotations. So this will export everything, even if we didn't approve it. And then we have train test split. You can just leave this as default probably. I'll talk more about what the train test and validate split is if you don't know when we get to the code part, because we'll actually be reading in our data set and training. And that's when this is important, is when you're training the model. So I'm just going to hit export now. You'll get a little pop-up. It'll also send you an email. And you can close this. You'll get a notification here It might take a second to show up because like the push notification part. If that's happening, just hit refresh on your page and then it should pop up. You can see this is the one I did just 13 seconds ago. And you can hit download export. This will just give you a zip file. Inside that zip file, you have a folder that's img or image. That's where all the images are stored. Just long file names now. And then you have a JSON files, which if we open up this training one, it's going to look really ugly. But all this is doing, like, it's great. You don't have to read this. The Cocoa import function will do that for you. These are all just kind of coordinates of the annotations we did and what images they belong to. So it'll read this in, it'll understand like, oh, draw these boxes or polygons around these images. And that's what I'm going to look at when the model's being trained. So don't worry too much about it, but there's just the JSON files that point back to the images. All right, so we're going to get in the code section soon. I know there's some other questions in the chat, so I'm going to catch up on those. I'm going to share the link out to the Google Collab, just so everyone can open this up. And then I'll try to catch up on the questions. So you want to go to this link, and you should get to a page that looks like this. And once you're here, go to File and Save a Copy in Drive. This will make your own copy of this, and you can edit it. You can do whatever you want with it. You could bookmark this original link if you want, because if you accidentally mess it up, you can always come back here and start over from scratch. So I'm going to catch up on chat. Also, if you have any questions, put them in the chat right now as people are doing that. So go to that link, go to File, and go to Save a Copy in Drive. And at least one person let me know if that worked for you, if the link worked for you or not. Oh, someone asked if the tool is made by our company. Yeah, so this is this labeling tool is made by Plainsight. I think I answered the high contrast with Smart Poly. Again, try it on your data. I think you might be surprised in what it works in. I know at least I have been. Someone said, can the polygon snapping be automated? So I think I kind of covered that with the auto label part, where it's automatically drawing polygons like we did with the car example. Someone said, in detection work, do we need to label non-positive data, say non-bird? A lot of the times you don't, but occasionally you might need to. So I would say start with not doing that. And in this case, we're saying it's all geese or something. But then if you have examples that you're just always getting false positives on, like it's always detecting, a rock, a specific type of rock or something as a goose, and for whatever reason your model just won't learn it, then you could bring in maybe another label and saying like, this is not what I'm looking for. Also, just a note on that. So let's say that it was a rock or something like that was always being detected. You can actually go in and potentially add more samples of like that rock in the background to your data set. Someone said, if you want to integrate a computer vision model into a mobile app with like iOS, for example, maybe through an API, what tech would you say is needed in the background to keep it running? It does really depend on exactly what you want to do, but you could make something like an AWS server where you're running your model and have an endpoint at that someone can ping. I think Apple has a lot of maybe ML stuff specifically for apps. I've done more stuff in Android, so Google has their whole Android ML kind of ecosystem. There's multiple ways of doing it. Sometimes you also want to run it on the actual device itself, not on the phone, or sorry, not pinging outside of the phone. So for example, like if you had a lot of images you're processing and you don't want to ping to an API every time because that costs a lot of money, you could actually deploy an app natively onto the phone versus like pinging out to the cloud somewhere. And again, if you are interested in kind of the whole deployment and or life cycle, you could also contact us if it's relevant to you. That might not be what you're asking. Oh, and here's a slide while everyone's doing that as well. So popular Python libraries for computer vision, there are so many of them, but here are a few that you might want to know about is like PyTorch. It's a library from Facebook for machine learning, popular in almost all the deep learning applications. Same with TensorFlow and Keras, except for it's made by Google. You have OpenCV. It's an awesome library for image processing and computer vision. NumPy is great at processing multi-dimensional arrays, which is usually what an image becomes when you import it into your code. And you have Pill and Pillow, which is another image processing library. Again, there's probably a whole bunch of them that maybe you're going to run into, but these are kind of the 5 really common ones that come up and that we're also going to use today. We're going to use a PyTorch wrapper. All right, so now that everyone is here, if you made a copy, again, go to File, Save a Copy and Drive. We're going to go ahead and run through this. So this is just some text portion here. If you've never used Collab, it's a way, it's Google's way of hosting a Jupyter notebook, which if you've never used a Jupyter notebook, it's a really cool kind of tool where you can write code and text and output visualizations all in one place. So like when we run our model on image, we can put it right here and it's not going to be a separate pop-up or anything. So you can double click into this. You can write some text here yourself and then hit Shift Enter to get out of the edit mode. And then you have code cells. So you could run this. There's a code cell that says print hello world. If you're not familiar with Python, this is just taking a string like hello world and then printing out, in this case, to our notebook. So if you ran this code cell, you should be good. It means you're connected to the instance. Oh, so you can hit this play button to run the code cell. You can also hit Shift Enter when the cell is highlighted. So you might see me a lot of times just hit Shift Enter like this, see the cell running. You won't actually see me click it. Google Colab is also kind of cool because it's not just like a Jupyter notebook. It's actually a whole Ubuntu hosted instance. So you can actually run bash commands. So I'm doing the exclamation mark and ls, which is listing all the items in directory. So you can see there's a folder called drive and a folder called sample data. So let's go ahead and install these dependencies. I'm just going to hit enter here. Someone mentioned in the chat this is taking forever. So sorry about that. Let me see why. Oh, so I think that Google has updated. So this is one thing that's kind of interesting and it's cool and bad sometimes about Google Colab is that it comes pre-installed with a whole bunch of different common like machine learning libraries. So I was like TensorFlow, PyTorch, all these things pre-installed, but it'll update to the new version sometimes without really notifying you. So this workshop, we're using PyTorch 1.8 and a specific version of Torch Vision. And the reason why I have this install here is because if I didn't do this and we just ran the rest of the code, even though there's a version of PyTorch installed, it may not work with our code. So I kind of have this as a failsafe, which I'm glad I did because I did not check this before the workshop. So they probably updated to like PyTorch, 1.8.2 or something, and I only verified that all this code runs on this specific version. So sorry if this takes a few minutes to install, but it'll be worth it because then everything should work afterwards, which will be great. And it's a good thing to keep in mind if you are using, if you're using Google Colab, that you might build something in here and then it might stop working if they change the dependency. But it's cool they have these pre-installed libraries so that you just hop in here, not really worry about setting up a TensorFlow environment or something and just start using it right away. So I should have checked this, but I did not, sorry. So it looks like there's a new version of Torch Vision, which is the vision package for PyTorch. And mine is done. Hopefully everyone else's is done if they're running at the same time. I'm going to hit Shift Enter on this next one. We're installing PyYAML and PyCoco tools, and we're importing Torch and Torch Vision. And this is actually some checks to make sure it was the correct version. And you can even see I have an assert here saying, does it start with 1.8? Then we can install Detectron 2. That's what we're doing here. So Someone said they weren't able to mount a drive. I think we'll get to that in a little bit if it isn't working for you. Hopefully. So we're installing Detectron 2. And don't worry about, it says I may need to restart this. Don't worry, I don't think you'll need to restart once we install anything here. I'm going to hit pip install pillow 7.2, specific version of pillow we want to use. And then here, I'm just importing all these different dependencies from Detectron 2. If you've never used Python before, this is like we downloaded those libraries. Now we want to import those libraries so we can use them in our project. And a couple other ones, like we're importing NumPy. CV2 is OpenCV. And creating a data set, we've already talked about this. So downloading the data set. So here's the data set that I've already labeled that we're going to use to actually train the model today. So you can just run this cell. It's going to go to this GitHub repository. It's going to download these 143 images, but there's multiple instances of geese in almost every image. And then again, if you do the ls command, the list objects or list items in directories, and we look in this goose object detection dataset folder, you'll see that there's the image folder, the test and train and validation JSON, just like we saw when we exported our dataset. If we look in that image folder, you can see here's a list of all the different images. Right, so importing a data set. So this might be what someone was talking about in the chat. So for this workshop, you don't have to worry about this. You don't have to change these environment variables, but I just want to talk about it because if you go on to train your own model, you make your own data set and then you want to be able to upload it and use it in this like notebook to train your own model, you'll need to get your own data set in. And you could do it if it's not giant or something, you could do it through kind of Git like I did here. I just made a GitHub repository. I threw the images up in there and then I Git clone it down. But what you might want to do is just upload it directly to Google Drive. And there's a couple ways you could do that. One, if you hit this little folder icon here, it'll open up the sidebar. You could then go find where those images are in your computer, click and drag them to this section, and it'll upload them for you. So it'll say, hey, you're uploading 200 images or something into this Google Colab instance. What's hard about that is that if you do this, or what's annoying about it, it's not hard, it's actually easier. But if you do that, then all of your data that you upload is going to be gone every time Google Colab like disconnects. So you can be in this and run it for like 12 hours a day or something like that, which I didn't mention. You actually get free GPU time, which is why we're using it to train our model. So if you go change runtime type, you can select a GPU or a TPU or none. And so you get like up to 12 hours a day for free, but it will disconnect. And so when it disconnects at some point, you'd have to re-upload your images again. So one thing I would do is connect to Google Drive. And I'm already connected here, but you can hit this icon if you aren't mounted to Google Drive and connect to your own Google Drive. It'll give you a prompt, like it'll make a code cell. And it'll give you a little prompt in there and it'll say, hey, copy this like token over or something like that. Again, you don't have to do it right now. I'm just telling you so that when you want to connect to your Google Drive, you know how to do it. Once you follow the little prompt, it'll connect to your drive and it'll show up here in this kind of drive section. And then you could create a folder here and upload images to that folder and then connect to it every time. So here, this is actually in this isn't in a Google folder, but if this was, I would just navigate to where my data set was in Google folder, and I would hit copy path and then paste it here. So I would find that JSON file, and then I would just copy and then paste it. And that's how I would update this if I wanted to connect to Google Drive. Sounds a little complicated. So sorry if this sounds like off-putting to people. Once you do it, it's really not that hard. And if you do have any problems, let me know, connect with me in the Slack channel or on LinkedIn. Again, you don't need to do it for this workshop, but just mentioning, that you'll probably want to do that so that like, if you want to keep retraining or something and come back to the same project, you don't have to download it every time, whether it's from Git or upload it every time into this instance. You can automatically connect to your Google Drive. So once you get it set up once, it's pretty easy. Sounds complicated. but if you get through it, you should be good to go. You could also just Google, how to connect to Google Drive from Google Collab, and there's a whole bunch of resources for it. So from here, we're going to import Detectron 2 datasets and import registered Cocoa instances. Like I was saying, a lot of frameworks have these Cocoa functions, so automatically know how to read in a Cocoa dataset. That's the one that we exported, remember? That's what I did with these geese as well. They're in the Cocoa format. So I'm creating 3 datasets right here. One is our training dataset, one is our validation dataset, one is our test dataset. So this is the variable or name that we're going to give it. And then we give it the path to those JSON files, which remember is like the maps of our labels to the images. And then we give it the path of the images. In this case, because if we were to look at our JSON labels, the paths all have that img / image name. So we actually don't include the /image, which is something tempting to do here. And then because that's where all the images actually live, we're one folder up from that because it's looking into that /img. So when you upload your dataset here, just remember that if you put in the path and it's pointing at the /img, it actually won't be able to read the image because it's looking for another folder called img in there. So go one folder above that. So if you ran that registered our Cocoa datasets, go ahead and run this code cell. And what this is really just doing is getting a random sample of our dataset and writing out our labels so that we understand that we read the labels incorrectly. This is actually super important. So I've been in instances before, especially if it wasn't as cut forward as just using a Cocoa dataset and then using a Cocoa function to read it in. Sometimes you might have to export to a different type of data or create your own custom data loader or something like that. And then so once you read in your, once you read in your data set, it's important to look at a few to make sure you read them incorrectly. So like, are these rectangles around the right things? Yes, they are in this case. But I've done it before where I accidentally, messed up a coordinate somewhere and the rectangles were like written backwards or whatever. So like it would be over here and our model would learn nothing from that. So here we're just creating a variable called my dataset train meta. I think we use this later. We're getting like the classes like goose out of it here. And then we're creating dataset dictionaries. That's what we'll use that later too. That's essentially just all of our data. We'll look at that in a second. And then we're just saying for each sample in the dataset dictionary, for 3 of them. So for 3 random samples, use OpenCV, read in the image, and then use the visualizer function from Detectron 2, and essentially just write out these visualizations here. If you look at that dataset dictionary object, you can just see this looks really crazy. Again, you don't have to worry about it though, but this is just our annotations. In this case, they're bounding boxes, so it's just 4 points for each rectangle, and then they belong to they each belong to an image. So when you give this to our model, it's going to say, look at this image here, and then look within this box. That's what you're going to be training on. Any questions so far? Again, if you've not done a lot of Python, it can seem a little bit scary, but don't worry. Go through this and you'll be able to train a model, which will be cool. Someone said they have a problem importing Detectron 2. If you do have a problem, try starting from the top again and shift enter or play button, because if you do them all in order, you shouldn't have a problem. We should all be kind of on the same instance. Someone said, can we do fine grain labeling, like doing differences between ducks, geese? Yeah, oh yeah, so this example, I just showed geese, and I think even a lot of the labeling examples, I might have just shown one object per image, but totally, you can do things like a goose or a duck. You just need to make a label for each one. So like in the example, when I made all those labels, right, I made one for like cups and geese. You would do the same process. So if you're going to do one for ducks, geese, and swans, you would go into your labeler, and when you set up your labels, you would just make a new label for each one of those. Someone said, would I just need to be more careful about polygon tracing? I mean, you would give it a name and then do the polygon tracing or auto label on it or something. So, so maybe you were talking about in here, like the auto label for bird. That would be tricky right now because we only have one generic bird thing for all those different classes. You could do it auto label for each one, like the duck, swan, or whatever, and then delete them. But right now, I would just do something like go into the labeler and use smart poly and manually distinguish them, probably is the best way. Someone asked, where will this be recording be? Where will this recording be posted? So it'll be posted on our YouTube. You can go subscribe here. All right, I'm gonna keep going on just so we can get through all the code, and I will be hanging out. So if anyone has any other questions after this, let me know. Someone said their notebook was frozen. That's interesting. So so if you go to runtime, you could hit restart runtime and run all. All right, so let's keep going here. This I linked to kind of where this function comes from. So one kind of annoying thing about Detectron 2 is actually that there isn't a built-in way to do validation while you're training your model. I'll talk about that when we get to that point. But here we're just creating our own Python class, and we're going to use this as we train our model. Essentially what we do, well, I'll talk about it. Let's go ahead and run the next cell because it's the longest cell to run, I think. And I'll talk about what's happening on. So go down to the next cell and go ahead and start this training process. And just 1 second. All right, so what this is doing is basically we're creating a class that we can call while we train our model. And it's going to say, you know, we're training our model on a training data set. And as it's training, we're going to have a look at a validation data set so that it's essentially the model's pretty much always going to increase accuracy on the data that it's seen while being trained. And we want to make sure that it's generalizing well on data it's never seen before. So we have a separate data set that's not looking at while it's learning, but we'll run it every, like in this case, we're going to say every 50 cycles of through our data, we're going to look at this other data set you've never seen before and see that you're still doing pretty good job predicting that, predicting the results on that new data set. And then, so what's happening here, this is the way you set up a model in Detectron 2. We have this kind of CFG or configure variable we're setting up from get CFG. Then we're saying CFG merge files, or merge from file. This is, we're selecting what type of model we want to pick. So I have some links up here. If you go, you can read more about this in the kind of the model zoo, which is what they call where they keep the different labels for, or the different models for Detectron 2. In our case, we're using a faster RCNN for COCO detection. And then we're going to use transfer learning. So if you change this to a different model, you'll want to change this as well. This is just saying, hey, we know there's pre-trained weights. So again, we're not going to start from 0 here. And so we're taking those pre-trained weights for this specific type of model. This is really important. So however many classes your dataset has, someone asked about doing something for like a duck, swan, and stuff like that. You would change this to however many classes. So in this case, we're just doing geese. So it's just 1, but if you had duck, swan, and goose, that would be 3. So we want to change this. This is our training data set. That's the variable we created when we made our data sets up here. So if you change this, you'd want to change that as well. You don't need to, though. You can just use that default. Max iteration, so this is how many cycles it's going to look at our data. So we're using 300 here, but you might need to really increase this depending on how complex your data is. You might need to do like 500 or 1,000 or more, but 300 is actually going to work pretty good in terms of geese. But a lot of geese look very similar. And then these are some more advanced things you don't really need to worry about, like number of workers, but you can do distributed GPU training and stuff like that. But you don't really need to change these most of the time, probably for your project right now. And then we're creating an output folder where we're going to save our model at. And then this is the validation data set. So it's going to say every 50 cycles here, go look at this data set and see how you're doing it and run some metrics. So we look at this output here. you can see that this is the output from the validation data set. If I scroll up, it's going to be very low at first. And then as it's going, it's going up. And that's what we want. This is AP, average precision. It's a metric for something like object detection or instant segmentation. I have a link to this later in the notebook about a little like a deeper dive into what this all means. But typically, the higher number here, the better your model is. So you want to see it go up. You'll see some other output here. This is actually kind of the ResNet model behind the scenes, the convolutional neural network. And you can see that it read in our 110 images from our training data set. And within that 110 images, there was 260 instances of geese. And out of the validation data set, there's 37 images that we're looking at. So the validation data set, because it can be a little confusing at first, you have the training data set, which is what your model's learning from. Then you have your validation data set, which is what we're kind of like, as our model is learning, we're making sure that it's looking good on data it's never actually seen before. But that alone can kind of affect how you tune the model. So some of these parameters we might change, like our learning rate or max iteration or something like that, just based on how it's doing in this validation data set. So I kind of like to view the validation data set as the training data set for the human in the loop in this process, right? Like if we saw it wasn't doing good and not generalizing, we might come and adjust these different parameters. And then when we feel pretty confident with our model, how it's doing on the validation data set, then we can run it on the completely separate test data set. All right, this is taking a little bit of time. How's everyone else's doing? Is it, are the numbers going up here for you? Is the model training? Is it the first time you've trained a computer vision model? Someone says keeps freezing. Don't worry, someone said their interview went out, or their internet went out, and I'll post a recording. So again, you can go back here, but also if you have the link to the notebook, you can catch up by running all the cells. But also if you just go, so let me get the link again for you as well. So here's the link to the notebook, and remember, just go to File, Save a Copy in Drive. And you could actually follow along for the rest of this and train the model. And essentially just labeling. We did the labeling part, and then we're training the model now. All right, so my model stopped training, and it looks like it got up to 78 in this case. And I'm going to go ahead and run this next cell. Sometimes people say in the workshop that this cell doesn't work, but most of the time it does. But if it doesn't, don't worry, it doesn't affect any other part of the workshop. This is running something called Tensorboard. It's kind of a cool way to see the output from your training. Oh man, maybe in my case, it's not going to work this time. That's a first. Give it in a minute. Okay, now it's coming. So you're going to see some stuff. It says like bounding box, B-box, AP. Someone asked, what does AP stand for? AP is average precision. There's a link a little bit later down when we get to looking at the test results. And that does a really good job of explaining it. But essentially, right, if you're measuring accuracy of bounding boxes, it's not just doing something like classification accuracy where you can say, was this true or false? You have to see like how bad was it versus the ground truth label, right? So if we labeled all the geese and there's a bounding box around it and the model predicted the bounding box is shifted way over here, or there was like way bigger or something, that's kind of something you measure to see how well it did. So like it might be overlapping to the ground truth bounding box that we gave it in the label, or it might be way off. So it's kind of something to do with that. And then there's the different kind of measurements. Again, there's a link I'll give you in a minute that dives really deep into this. So there's different ways of looking at average precision, like how precise does it need to be? And so these are all kind of different scores automatically generated from that. So the straight up average precision here, it says 78, and then all these other ones are higher because it gives like a higher threshold. But you can see that our average precision is going up, and it looks like it's still going up. It didn't really even plateau out too much. So if we train for more iterations, it might actually go up further. So like maybe we want to do 400 or 500 iterations. And then you'll notice when you train models and you're looking at things like accuracy or AP, that at a certain point, per cycle, it's going to get, it's not really going to learn too much more from it. So it's going to kind of plateau out versus going up. You can dig around at other stuff in Tensorboard too. So like if you want to see more of these different things like accuracy or loss functions, you can look at those graphs in here, which is kind of cool. All right, so now we have our trained model. We're going to hit Shift Enter here. We can look in our output folder. You could also, again, open up this little file, navigate around in here if you wanted to see output. See this model underscore final.pth. That is our final model that is trained. And again, we're kind of doing this little config setup thing. So we're saying CFG is equal to get config. We're setting up a model again. So we're like, we have our model, it's trained. We want to bring in the model now and use our new weights on it and then run it on an image and a video. So in this case, we're saying, merge from model zoo, just like we did before when we were just like setting up our model. This needs to be the same as whatever model you trained on. So if you trained on this model and then you had a different name in here, it's going to throw an error because it won't know how to handle the weights that we're going to feed into it. And then instead of before, like we used the transfer learning, we said load these weights from this kind of URL, like from the Detectron 2 place. Instead, we're going to say load in our model. So if you saved your model to a different place or you moved it out into a different folder, like into your drive folder, you can just copy the path to it. And that's exactly what's happening here is, it's just looking at this path of where the model is. And then test data set. This is so that we can run a test on it after we did our validation data set. And we were like, cool, that looks like a good average precision. Let's do it on a whole different data set that I didn't mess with training or I didn't look at it when I was doing anything with training. And then again, this needs to be how many classes you're looking for. So someone asked about the duck, swan, goose. That would be 3 here again versus 1, which is just geese. And then here's our ROI threshold. So the ROI in this case isn't return on, or is a region of interest. So not return on investment, which is the other common ROI. And this is saying that only draw out the prediction if you're this confident that it is the thing we're looking for. So this is saying if you're 90% confident it's a goose in this case, draw it out, like count it as a goose. But if you have a much more complex data, you might want to lower this down. Like if you have this as 90 at first and you're not getting any predictions return on these outputs, lower this down to like 60 even and see what happens and then higher it up again. But you'll notice like if you go really low on a lot of models, you could do like 30% sure. It might think all sorts of things are a goose, like a rock and whatever. So you want to have typically some nice threshold that's like only when you're this confident, draw the prediction. And then we create this predictor variable, and this is we're going to pass this the image, and it's going to do a prediction on it. So let's run that cell. Run this next one. This is just creating a variable test image path, and we're grabbing an image from our test data set, so it's not one it saw while training. Then we're using OpenCV again to read in the image, and then we're going to get outputs from the predictor. So we're feeding our image into the predictor, and then we're setting the visualizer. We're scaling the image, and then we're drawing the output here. So I'll talk a little bit more about this, but we're getting the instances and then just kind of visualizing those out. So we'll see what this looks like raw in a second, but let me know in the chat if this worked for you. Did anyone run this image predictor for object detection? Someone said they were getting an error. Interesting. I could troubleshoot with you hopefully after this if you want to, but again, most of the time if there's some error, just make sure that you ran every code cell before this. So if you didn't run this one, for example, this code cell would not work. And most of the time when someone has an error, and I've done this a lot too, where I accidentally just skipped over one if I'm manually running them all, this might not work. one thing you do is like restart the runtime and run all the cells. And if you hit run all, this will just run all the cells in order. Also, so a lot of people said it worked. That is awesome. And if you never did computer vision before, or if you've never done object detection before, this is your first model potentially, and that's super exciting. So we're running on images here. Essentially, what we want to do next is we'll run it on a video, which is really running it on a sequence of images, right? Like if you break a video apart, it's a whole bunch of different frames. All right, so if we print just the image variable, like we read in an image with OpenCV, you can see there's just this really big array. Like I was saying, images really just become multi-dimensional arrays. And then if I print out the outputs, which is like we fed our predictor function the image, it returned outputs. And you'll also see this 2CPU. This is really common in PyTorch. So when you're running a model, so if you're doing a prediction or training a model, you're using the GPU, but then you usually want to move stuff off the GPU memory back to the CPU. So you can do things just like run code normally, not on a GPU. So if you see something like 2 device or 2 CPU, that's kind of what's happening. So in this case, we're getting our outputs we're printing out our outputs here. And you can see this is all the stuff returned from our model. So we have number of instances is 2 because we have 2 geese. We have the image dimensions. Then we have some other fields here. We have prediction boxes. So this is actually the data, right? Like it's just 4 points drawing out a rectangle. This is actually the data of saying like, this is where I think the goose is. And then we have here the confidence, it's 99% sure for one of them, 98% sure that one's a goose. And then the predicted classes here is 0. So the classes always kind of become numbers in this case, where it's like 0 or 1. We can associate 0 with the goose because there's only one class here. But if it was like the goose, ducks, and swans, 0 could be goose, 1 could be duck, 3 could be swan. Python, like most programming languages, starts indexing at 0. Someone asked, why are they getting different colors? This color right now is just kind of a random generated color from the Detectron 2 visualizer as well. All right, so let's go ahead and, and one thing I wanted to note, so it's awesome to like see this data, visualize it, right? Like where are these boxes drawn and how do they overlap and stuff like that. A lot of the times in the code though, if you're actually making decisions based on that, but you don't need to actually visualize it, you use this data and you could do something like, well, do these coordinates overlap with these coordinates? Is that like a collision or whatever you're trying to do on there. So you don't always need to write out the visualizations. Like we as humans love it because it's awesome to see, but this is actually really important to make decisions like with your code. Or maybe you want to look in here and be like, how many geese are in the frame of this video? If there's more than 5, send me a text or something like that. Or for measuring occupancy in a room, right? You could be like, just how many people am I counting in this room? So let's do it one more time. But this is just an example of that. We're just getting how many geese there are, and then just printing out how many there are. And often that's like a lot of times, or a fair amount of times, what people are looking to do. Like if they just want to see how many things are in a frame or something, you can actually solve that pretty easily here. Let's do one more image here. And see, this is geese photoshopped into my living room. And then there's actually a reason behind this. I can talk more about it later, but this data set is has some synthetic images where like it was detecting chairs as a geese in my living room because it never saw a chair before when we trained the model. Just like I was talking about how if you have certain rocks or something like that that are getting mispredicted as geese, you might want to add those into the image or make sure you get images with the goose and the rock in it. And there's a way of you can kind of synthetically create images. In this case, I Photoshop stuff into my living room. All right, so let's quickly do evaluation metrics, and then we'll run this on a video. So here's a link. Someone was asking about more about average precision or AP. You could read way more about it here. You should be in this notebook, so you have all these links you can come back to as well. But this talks a lot more about what's going on and how to measure the success of things like object detection. So we can run this. This is essentially just importing some evaluation functions from Detectron 2, and then we're passing it our test data set, which we haven't looked at yet. And then it's really just running the predictions on it and seeing how well it's doing. So just like we did with the validation data set while training, this is our separate holdout one where now we feel confident that it's looking good. Let's see how well it does on a new data set. And you can see that in this case, the average precision 79 and all the way up to 99 on this AP50. So this is a great easy way to just kind of be like, how good is my model doing? All right, so let's go ahead. We only have a few more code cells. We're just going to run this on video, and then I will just answer any other questions that I didn't get to yet. So you can run this cell. This is just kind of displaying this YouTube video. I just have a video of some geese walking around. Cool. And here we're going to install another library. Install YouTube DL. This is going to allow us to download the YouTube video. And then here, we are just, I installed the library. Now we're actually running it. I'm passing it my YouTube link here for my goose video. And then it's going to download the video here. And then we're not actually going to use this, so you can skip this code cell if you want. But this creates a new video out of that where we can say, like, I only want the first 6 seconds of it. This is really nice to do sometimes, like before you run your model, because it can take a little bit to run the model and write it out on the visualization. If you're running it on like a minute video or something, you might want to do something just like a quick 6-second clip before that. So that created this video clip that you could change this path out for this video clip one. So I could hit copy and just paste it in here. And then this would only run on that 6-second clip. In this case, our video isn't that long, but I just want to point it out because I've been in cases where I wanted to run this on a minute-long video or 45 seconds or something, and it took too long to write it out. So instead, you could just do like a 6-second clip. So I'm going to run this, and while it runs, we'll come back and revisit it. So just go ahead and run this code cell. Should get some output here. It looks like it's working. All we're really doing here is we're importing some stuff again from Detectron 2. The visualizer library is the thing that writes out those rectangles and colors. And then we're using OpenCV to get some, we're reading in the video that we want to do, and then we're getting some metadata about the video. So like how many frames per second, and like what's the width and stuff like that, number of frames. Then we're using OpenCV. They have a thing called Video Writer, which is how like we're going to take in a video and then we're going to use Video Writer to output the video. So we're passing in some variables or settings here where we're going to write it as out.mp4. Source is going to be mp4. It's going to be the same frame width, frames per second as the original video. And then we're creating a variable for the video visualizer, which again gives us some stuff to write out, like the rectangles and stuff like that. And then we have a function here that is essentially just a while loop saying, while there's still frames in the video, use that predictor, pass in the frame. So essentially saying, while there's a frame, take the frame, run the predictor on it, and then we're going to visualize that frame and write it out with OpenCV. And then when the frame is done, go ahead and break. And then this is that for loop. So it's the same for visualization in the video, run, just keep running it until we're out of frames. And then here's the video.write portion. And then this is kind of an OpenCV, you close out things like just video writer.release. And then go ahead and run this last code cell. It might take a second here to download. Let's go. I think I did this earlier, so it might have a pop-up or something too. Sometimes, like if you download more than one video, you'll get a pop-up saying like, do you want to download more than one thing from Google Collab? I'm seeing some reactions. People are saying they're getting their video. I don't know why mine is taking so long. Usually it's much faster than this, so I don't know what's happening with me. Everyone's saying theirs is awesome, and I'm still waiting over here. Better than the opposite, maybe, though. Like, I'm glad you are getting your results. Someone asked, how do you get to code view? Can you clarify the question? Like, how do you get to code view, like in Google Colab? Well, I mean, what is the, do you mean like for the text here that you can double click into it and then shift enter? Otherwise, these are code cells and it should already be a code view. Again, I don't know why mine is taking forever, but I can see a lot of you already have your video. So it sounds like this worked for a lot of people, right? That's awesome. And again, if this is your first time doing something like object detection or even computer vision, give yourself a round of applause, because it's hard to go from like not knowing anything about data annotation or labeling, seeing that whole process, and then there was a lot there, and I know some of it we probably went through very fast. So if you've never done that before, you probably want to go revisit either the code or resources. But you went from maybe even knowing nothing about it to going through and actually training a state-of-the-art object detection model on geese. So it's really cool. Hopefully you learned something new, and hopefully you had a lot of fun. And I'd love to see, like, if you go build this on your own data set, or train a model on your own data set. I'm always happy to see it. It's always really cool. So feel free to tag me wherever you shared that. If you put it on LinkedIn, Facebook or Google or Twitter or anything like that. I always love seeing it. It's really cool. So here is my video finally. I don't know why it took me so long. You can see it's running detection on geese and drawing rectangles around them. Awesome. So I'm going to stop the recording, but I will be hanging out and answering any other questions. I know there's still quite a few people in here, and I think there's some questions I did not get to yet. So let's just stop the recording, and I'll be here to answer those questions.